All right, so we're going to winding things up here for this week's lecture. Don't forget, there's still some additional um, uh, things for you to do on the to-do list for this week. So, misleading statistics. Here's an example. It just kind of illustrates it. Should you avoid using misleading data visualization just to support your argument? As you can see here, it's actually 50-50, but the way they set that bar graph up, it makes you think that yes, we should avoid using it. But in reality, that's not the proper way to present that type of data. So I mentioned at the beginning of the lecture to watch this video clip. It's a really good one to watch that kind of really illustrates this issue of misleading statistics. Another good book to look at is Freakonomics. I imagine many of you are familiar with this. You can subscribe to their podcast. I know they've even got a second book out. But these guys they're really cool, and it's fascinating to read their books. What are some sources of misleading statistics? Well, you can collect bad data, you can make bad graphs, you can do incorrect analysis, and you can interpret things wrong. So we got a lot of opportunities to screw things up. So here's an example. 30% of students hate taking polls. Maybe you hear that or you read that in a school newspaper. The problem is you gotta get a little, the devil is in the details. What was the population that they sampled from? Well, they only surveyed 10 students. And it happened to only be the 10 students that were eating in the cafeteria that afternoon. So is that really representative of the population? No. So that's an example of sampling bias. The classic example of sampling bias came from the election of Truman, where the newspapers predicted that Dewey would defeated Truman. They were so sure that they published that before the final results came out in the and they did that. They published it in the Chicago Tribune, and this was Truman in his parade, or coming out and showing it. And in fact, what they did was there was a classic example of sampling bias because the sample included too many Republicans. Because at the time, Republicans were the people with all the money and more likely to be surveyed in a poll than Democrats. Here's a website. You guys write this down, take a look at it. It's a great resource that helps illustrate misleading statistics, and it's called Lies, Damn Lies, and Statistics, a data literacy primer. Spend some time looking at this website. It doesn't take very long. But you can see here, this was what we just had go on in our recent elections. Where, if you remember, the polls were saying that, oh man, well, initially they said that Hillary Clinton was going to win, and obviously we found out that Trump won. But here, you remember back, even though Trump did in fact legitimately win the Electoral College, he lost the popular vote. However, Breitbart published this on their website and saying that Donald Trump won an overwhelming 7.5 million popular vote victory in 3,084 counties. Of the counties, 3,141 counties or county equivalents in America. So they were skewing, making it look like he won all of that. Well, in fact, the correct figure is on the right. And in the days following the election, we found out, in fact, he lost by 3 million votes. But by the time Breitbart had corrected the story, it had already been shared 35,000 times and liked 59,000 times. And the uncorrected piece was never taken down by Breitbart. And so this is a prime example of misleading statistics. And in fact, this was completely wrong. And they kind of skewed it like that first figure I showed you. Here's another one that when you read, watch that YouTube video I talk about. She talks about this video, this example. So the graph below was shown by a United States congressman to convince people to defund Planned Parenthood. So if you look at the figure on the left, you have the y-axis would have been number of people. The x-axis would have been the years that they have on there as they're going through. It's over time. So it looks like over time abortions went way up whilst cancer screening went way down. However, if you look at the numbers, they're really not that much different. So if you really put them they're using two different y-axes here. And what they did is they overlaid the two graphs without using the correct scale. So when the correct scale isn't used, and in fact, it shows that rate of abortions has been fairly flat since 2006, whereas cancer screenings have gone down over time, but it's not the same relationship. So they're I mean, this is falsifying data, but I guess in Congress they can do that to make their point. And people just take them at their face value. And so that's why you guys are getting your DNA piece, so you can be very fine consumers of data, and you can question those things and understand what's going on. Here's another example of a misleading graph in statistics. So you can alter the graph by altering the scale. So here on the y-axis, if you look at the figure on the right here, let me get to it. They've, in fact, did 4, 5, 6. So it makes it look like there's really dramatic differences. In reality, they're what? They should have really used this. The one on the left is correct. The one on the right is incorrect. Another thing is with polls or surveys, is how you write the question is very important. There's very much a science to writing survey questions. Read this one. On which issue does the mainstream media do the worst job of representing Republicans? So if I was to venture to guess, this was probably done by some right-wing leaning group. Just by reading that. Because remember, see how they're using worst job. That's not a really, that's really kind of, it's a loaded question. So it's not very accurate. It's a leading question. Another way is we showed a little bit earlier when we talked about data mining, but a wrong analysis is correlation does not equal causation. Let me say that again. Correlation does not equal causation. Here's an example of is to demonstrate ways that the relationship between correlation and causation are abused. This is another one from Tyler Vegan's blog, where he showed it looks like there's a relationship or correlation between people who died from falling out of their bed and number of lawyers in Puerto Rico. It doesn't even make sense. So you can see how easy it is to intentionally skew data in order to make a dubious point. When can we imply causation? Really only with experimental designs, and even then we cannot prove what we found. Because experimental designs help minimize the risk of confounding variables. What's a confounding variable? Well, confounding variable is, or an extraneous variable. Well, an extraneous variable is an undesirable variable that influences the relationship between the variables of that an experimenter is examining. A confounding variable is an extraneous variable that vary with the levels of independent variable that are most dangerous type in terms of challenging the validity of experimental studies. Confounding can also be considered the confusion of effects. It's when another factor may have influenced the results of the study. It's possible that there may be some other variable or factor that is causing the relationship between the variables under study. Say for an example, here's some examples of a confounding variable. So CRNA does a study on post-PONV. It finds drug A significantly decreases the rate of PONV when compared to drug B. However, when he did his analysis, he found in fact that the group that received drug B required significantly more perioperative opioids, so that's why they puked more. So the confounding variable was perioperative opioids. So when you guys are going through doing your literature reviews and critiquing your articles, be careful, be very particular in looking at their descriptive statistics and their differences between the groups, using their table ones, to see if there's any differences in baseline characteristics or key variables that may potentially confound the outcomes. And finally, just to wrap things up here, here's some examples of some statistical software that you may be familiar with or you may read about in the literature. The most common one I've used is SPSS. Another one is SAS, Stata, Minitab. Excel, you can even download some special drivers that allow you to do some statistical tests. As a matter of fact, let me show you really quick that if you have Microsoft Excel 2016, which I got through Office 365 through the university, it actually has a data analysis pack in it. Let me see if I can show you how to do this. So if I go to data, let's see, tools, data analysis. So you can actually go into Excel add-ins and you can click analysis tool pack, and what that would do is if I went and did this, and I think it's some earlier versions of Excel it doesn't have that, but you can do this, and it actually in Excel allows you to do some simple statistical tests in there with this this software, but you have to add it. You can search this on YouTube how to do that, and it'll explain to you how to set up those drivers if you guys ever want to learn how to do that. But it is important when we don't go in, we'll touch on maybe in some of the later lectures on some of the nuances of the different statistical tests, but really we want you to understand the concepts behind them, not necessarily how to run them and what are all the assumption limitations of those tests necessarily, but in the context of how you can understand and be good consumers of the literature that you're reading, and be good DNAP students and really practitioners after you graduate. So with that concludes this week's lecture. If you have any questions, feel free to contact us. Either this year we're dividing the biostatistics course into two sections. Dr. Myself and Tito are dividing this up, and we're trying to keep the content the same. So certainly contact your faculty, and certainly you can always email me if you have any questions, even if you're not in my section. And with that, I thank you, and you guys have a nice day.